Hello, my name is Roger Moore, and I'm Professor of Spoken Language Processing in the Computer Science Department at the University of Sheffield in the UK. And over a large number of years, I've worked on many different aspects of speech processing, particularly speech technology. And one of the areas that interests me greatly, especially at the moment, is interactivity and how it is that human beings are able to engage in spoken language interaction with each other and also with machines. And part of my interest here is on how we model this, and in particular, how we view this as a potential form of entrainment between interlocutors. So that's what I'm going to be talking about, and I'm going to introduce a particularly different way of thinking about this, which is from a control systems perspective. So obviously, collective behavior has been very well studied, and I'm sure we're hearing a lot about that at this workshop, whether it's shoals, swarms, flocks, or crowds. This kind of interactive behavior has already been very well studied and modeled. I'm particularly interested, as I say, in speech and therefore in vocal entrainment, vocal synchrony. And it's not just human beings that do this, of course. Many animals and insects will interact in this way using sound. It's a very specialized form of interaction between humans. Here's some Inuit throat. That's two individuals very, very carefully entrained with each other. So I want to now distinguish between the different models and mechanisms for tackling this. So the models are typically based on coupled oscillators. Again, we'll be hearing a lot about that at this workshop. It's essentially based on dynamical systems and has an attractor space with some rhythmic aspects. There are some control variables which are kind of implicit. It's very much targeted at mechanical systems, rooted in maths, and is typically described by dynamical systems theory. But I want to contrast that with interacting control systems, which are also dynamical systems and also create an attractor space, but there are differences. So here they are. The control variables in control systems are explicit. And the argument is that this is much more suited to living systems. And this is rooted in cybernetics and indeed leads to a particular form of control theory, which is known as perceptual control theory, or PCT. So control systems have been used in collective behavior modeling, and the most famous is by Reynolds, his Boyd's arrangement for modeling swarms. And you can see the rules of his system on the left there. I say rules, but they're not discrete. They're continuous because they're control structures, and they basically allow continuous control of the steering of each individual agent. And that leads to some very interesting emergent entrained behaviors. So what is a control system? If you haven't seen one before, this is what it looks like in Control Systems 101. There's a reference input, which is what is desired on the left. The top line there is how that's actuated then into the real world by some mechanism. But the key thing is that there's a feedback, and that feedback is basically sensing the outcomes of the actions, comparing that with the intentions, and that generates an error signal. And it's the error signal that actually drives the behavior. So if there is no error, then nothing happens. But if there's a huge error, then something needs to change in order to for the system to regulate. So this is a very old-fashioned idea. This is Watt's steam engine, and you can see the thing with the balls in the middle is Watt's governor or regulator, which was a way of controlling this amazing piece of apparatus. The modern day equivalent is, of course, the thermostat, and the thermostat is a very neat mechanism which allows us to maintain the temperature, climate control, a room in a very straightforward way. And the reason these things are very efficient and work very well is because you're using what's called closed loop negative feedback control. In a living system, this would be called homeostasis. It's basically stabilizing an arrangement. This has been taken by Bill Powers quite some time ago now to be the basis of all interesting behavior in living systems. And his famous book, Behavior, the Control of Perception, essentially was an anti-behaviorist stance. I don't have time to go into that, but this is an interesting aspect of why I'm talking about this particular approach. So here are some research questions. What happens when two or more control systems interact? What are the variables and how do they actually influence the emergent behavior? And how is the emergent behavior also influenced by the topology of the network? In other words, how the agents are connected. These are very important questions when it comes to what's likely to happen from an entrainment perspective. So I programmed this in a simulation environment in a language called Pure Data, which is a precursor to Max MSP, which is the professional version that you'll find in most music labs. What you're seeing on the screen here is an agent with various sliders and controls. It's a vocalizing and listening agent. In other words, it can make sound and it can listen to sounds. Here are the inputs. It can be audio or it could just be a beat. It has outputs, which can be audio or a beat. And then the slider, so there are two embedded control structures. One is to do with maintaining synchrony with other agents. And there's a slider here, which is you're able to set the amount of effort, in other words, the attention that this agent pays to another agent. And the second control loop is essentially the same kind of idea. It's another attention mechanism or effort, which is now paying attention to its own rhythm. How much effort does it place on maintaining its own rhythm? These are very interesting variables. You can also change the vocalization. It can beep, it can make human noises, or a cicada or a bird, and you can switch the whole thing on or off. There are various parameters that are delivered as it's running. There's the period, the synchrony error, and the signal to noise ratio. So here's what it looks like in the simulation environment. And here you can see two agents which are connected to each other. So the one on the left is the leader and the one on the right is the follower. And that's because there's a one-way connection between the output of one and the input of the other. The environment has various controls up here. And then there are displays of the beats and the degree of entrainment. It's currently set up to beep. And this is what it's like. And what you're noticing is the follower is now in sync with the leader. Here's another arrangement. This time we've got a chain of 9 agents. So there's a leader at the front and then all the way down the chain. And here's a vocalizing a cicada. And then convergence from the control loops takes place, so we get more and more synchrony. Here's a different configuration. So we have 1 leader and 8 followers. So this is not a chain. This means that there's a more immediate possibility. And I've set this up for human vocalization. There's a caller saying oi. And the followers are saying "ow." And then the final demonstration is where we've got interacting agents. So this is mutual entrainment. So we've got connections running both ways, backwards and forwards between these two. And what happens here, notice that they're both self-centered at the moment, so they're independent of each other. The slider has just changed. So they're now listening to each other. And they're also paying attention to themselves, so they're both slowing down and trained. And there they're going to watch the slider has now changed. They're only interested in each other, not paying attention to themselves. If you look at the period and listen, you'll notice that it's getting faster, faster and faster. In other words, it's rushing, which is another classic emergent behavior. So I don't have time to go into all the experimental results. Simply draw attention to one in the middle, which shows that if you have a stimulus response chain, you get delays accumulating. But if with feedback control, you have very little synchronization error, but you have a lot more variance as you get down the end of the chain, because the agents at the end of the chain are, they're losing track a bit of what's going on, because in other words, noise is propagating down the chain. So in this short talk, I've demonstrated that interacting closed-loop negative feedback control systems is an interestingly different way of looking at modeling entrainment, precisely because it gives insights into how the different control variables and the connections, the topology of the connections, influences the behaviors. There are lots of other possibilities that could be approached here. I'm very interested in turn-taking, not as a stimulus response behavior, but as an emergent entrainment behavior. And this environment would allow me to investigate that. Cooperation versus competitive vocalizations, and indeed how communicative behavior emerges from interaction in the first place. If you want to find out a bit more about this, then you can go to my website, or there are a couple of papers listed here: Finding Rhythm in Speech, which is a response to a talk by Fred Cummins, and more recently, Vocal Interactivity in Crowds, Flocks and Swarms, which pretty much describes the environment that I was just demonstrating. And that's it, and I look forward to hearing any questions. Thank you very much.
Hi, thanks for a really fascinating talk. I'm feeding back a little bit.
Yes,
okay.
I'm getting...
Okay, I think it's tolerable. I have a question about there are two parameters in the model, one for self-centeredness and one for other-centeredness. And yes, those are separate. So sort of cognitively, attentionally, I guess I would think those would trade in some way. I can sort of put attention on myself or other, but maybe not both maximally all the time. But I guess on the model, they're completely independent, so you can do whatever you want with them. So I'm just curious whether there are sort of behavioral consequences for keeping those positively correlated instead of trading them, that would be something that you wouldn't see with humans.
Oh, that's very interesting you say that. This is where I'm very sad that I'm not there with you to discuss more about that over coffee. Because from my perspective and using the model, it would be perfectly feasible to have maximum attention applied to both at the same time in a sort of a dominance relation, really competing to interact with somebody else, but insisting on one's own behaviors getting through at the same time. So I'd certainly like to discuss more about why you think those would be traded rather than independently controlled. Or indeed, if you can point me at any literature which would suggest that, that would be very interesting.
Okay, I can do that offline, or we can chat offline.
Brilliant, thank you.
Thank you. Great question, Molly. Thanks. Are there any other questions from the audience here? Martin.
Thanks very much. That was a brilliant presentation. So I'm kind of thinking through how the model you've presented here might apply in the context of an ensemble musical performance. And it strikes me that within this architecture, one of the things that would be going on would be the participants or the musicians in that situation, where they would be getting feedback would be, does the whole sound like the whole should sound, as it were? So in a way, the attention might not be so much on self or other, the attention might be on the total outcome, and then on, how does my part have to change or not change in order to maintain the outcome sounding like it should do? I just wonder if you had any thoughts about that.
Well, the total outcome, of course, is the ensemble activity of the individuals. So in that sense, it's perfectly feasible within the simulation to have an agent which is listening to all of the other agents. So actually the last presentation was kind of very closely connected with what I was talking about, it turns out. So you can easily imagine how the agent an individual agent has to take into account its position with respect to whatever it's hearing, and that, whether that is the nearest neighbor, only one other individual, paying attention to the conductor, or to the totality of the behaviors that are taking place. All of those are possibilities. This is why I raised earlier in the talk the importance of the topology of the network of connections, again, which is very much addressed in the last talk.
Thanks a lot. Again, I wish you were here to discuss this more over coffee, but hopefully we can connect.
Unfortunately, heading to Dublin almost immediately for another meeting.
Well, thank you so much, Roger. Thank you for joining us.